Hello everyone, it's Caller from 19. Today is day 23, my challenge day, and what I'm going to do is third week of team learning course. Okay, let's start.
For these hyperparameters. In this video, I want to share with you some guidelines, some tips for how to systematically organize your hyperparameter tuning process, which hopefully will make it more efficient for you to converge on a good setting of the hyperparameters. One of the painful things about training deep nets is the sheer number of hyperparameters you have to deal with, ranging from the learning rate alpha to the momentum term beta, if you're using momentum, or the hyperparameters for the ADAM optimization algorithm, which were beta 1, beta 2, and epsilon. Maybe you have to pick the number of layers. Maybe you have to pick the number of hidden units for the different layers. And maybe you want to use learning rate decay, so you don't just use a single learning rate alpha. And then, of course, you might need to choose the mini batch size. So it turns out some of these hyperparameters are more important than others. For most learning applications, I would say alpha, the learning rate, is the most important hyperparameter to tune. Other than alpha, a few other hyperparameters I tend to would maybe tune next would be maybe the momentum term. I say 0.9 is a good default. I'd also tune the mini batch size to make sure that your optimization algorithm is running efficiently. Often I'll also fiddle around with the hidden units. Of the ones I've circled in orange, these are really the three that I would consider second in importance to the learning rate alpha. And then third in importance, after fiddling around with the others, the number of layers can sometimes make a huge difference, and so can learning rate decay. And then when using the ADAM algorithm, I actually pretty much never tune beta 1, beta 2, and epsilon. Pretty much always use 0.9, 0.999, and 10 to the minus 8, although you can try tuning those as well if you wish. But hopefully this gives you some rough sense of what hyperparameters might be more important. important than others. Alpha, most important for sure, followed maybe by the ones I've circled in orange, followed maybe by the ones I circled in purple. But this isn't a hard and fast rule, and I think other deep learning practitioners may well disagree with me or have different intuitions on these. Now, if you're trying to tune some set of hyperparameters, how do you select a set of values to explore? In earlier generations of machine learning algorithms, if you had two hyperparameters, which I'm calling hyperparameter 1 and hyperparameter 2 here, it was common practice to sample the points, in a grid, like so, and systematically explore these values. Here I'm placing down a 5 by 5 grid. In practice, it could be more or less than a 5 by 5 grid. But you try out, in this example, all 25 points, and then pick whichever hyperparameter works best. And this practice worked okay when the number of hyperparameters was relatively small. In deep learning, what we tend to do, and what I recommend you do instead, is choose the points at random. So go ahead and choose maybe the same number of points, right? 25 points. And then try out the hyperparameters on this randomly chosen set of points. And the reason you do that is that it's difficult to know in advance which hyperparameters are going to be the most important for your problem. And as you saw in the previous slide, some hyperparameters are actually much more important than others. So to take an example, let's say hyperparameter 1 turns out to be alpha, the learning rate. And to take an extreme example, let's say that hyperparameter 2 was that value epsilon that you have in the denominator of the Adam algorithm. So your choice of alpha matters a lot and your choice of epsilon hardly matters. So if you sample on a grid, then you've really tried out 5 values of alpha, and you might find that all of the different values of epsilon give you essentially the same answer. So you've now trained 25 models and only gotten to try out 5 values for the learning rate alpha, which is the thing that's really important. Whereas in contrast, if you were to sample at random, then you will have tried out 25 distinct values of the learning rate alpha, and therefore you'd be more likely to find a value that works really well. I've explained this example using just 2 hyperparameters. In practice, you might be searching over many more hyperparameters than this. So if you have, say, 3 hyperparameters, I guess instead of searching over a square, you're searching over a cube, where this third dimension is hyperparameter matters, randomly chosen set of points. And the reason you do that is that it's difficult to know in advance which hyperparameters are going to be the most important for your problem. And as you saw in the previous slide, some hyperparameters are actually much more important than others. So to take an example, let's say hyperparameter 1 turns out to be alpha, the learning rate. And to take an extreme example, let's say that hyperparameter 2 was that value epsilon that you have in the denominator of the Adam algorithm. So your choice of alpha matters a lot and your choice of epsilon hardly matters. So if you sample on a grid, then you've really tried out 5 values of alpha, and you might find that all of the different values of epsilon give you essentially the same answer. So you've now trained 25 models. and only gotten to try out 5 values for the learning rate alpha, which is the thing that's really important. Whereas in contrast, if you were to sample at random, then you will have tried out 25 distinct values of the learning rate alpha, and therefore you'd be more likely to find a value that works really well. I've explained this example using just 2 hyperparameters. In practice, you might be searching over many more hyperparameters than this. So if you have, say, 3 hyperparameters, I guess instead of searching over a square, you're searching over a cube, where this third dimension is hyperparameter 3. And then by sampling within this 3-dimensional cube, you get to try out a lot more values of each of your 3 hyperparameters. And in practice, you might be searching over even more hyperparameters than 3, and sometimes it's just hard to know in advance which ones turn out to be the really important hyperparameters for your application. And sampling at random rather than in a grid ensures that you're more richly exploring the set of possible values for the most important hyperparameters, whatever they turn out to be. When you sample hyperparameters, another common practice is to use a coarse-to-fine sampling scheme. So let's say in this 2-dimensional example that you sampled these points, and maybe you found that this point worked the best, and maybe a few other points around it tended to work really well. Then in the coarse-to-fine scheme, what you might do is zoom in to a smaller region of the hyperparameters and then sample more densely within this space. Or maybe again at random, but to then focus more resources on searching within this blue square if you're suspecting that the best setting of the hyperparameters may be in this region. So after doing a core sample of this entire square, if that tells you to then focus on a smaller square, you can then sample more densely in this smaller square. So this type of a coarse-to-fine search is also frequently used. And by trying out these different values of the hyperparameters, you can then pick whatever value allows you to do best on your training set objective, or does best on your development sets, or whatever you're trying to optimize in your hyperparameter search process. So I hope this gives you a way to more systematically organize your hyperparameter search process. The 2 key takeaways are: use random sampling, not a grid search, and consider, optionally, but consider implementing a coarse-to-fine search process. But there's even more to hyperparameter search than this. Let's talk more in the next video about how to choose the right scale on which to sample your hyperparameters. In the last video, you saw how sampling at random over the range of hyperparameters can allow you to search over the space of hyperparameters more efficiently. But it turns out that sampling at random doesn't mean sampling uniformly at random over the range of valid values. Instead, it's important to pick the appropriate scale on which to explore the hyperparameters. In this video, I want to show you how to do that. Let's say that you're trying to choose the number of hidden units NL for a given layer L. And let's say that you think a good range of values is somewhere from 50 to 100. In that case, if you look at the number line from 50 to 100, maybe picking some number of values at random within this number line is a pretty reasonable way to search for this particular hyperparameter. Or if you're trying to decide on the number of layers in your neural network, we're calling that capital L, maybe you think the total number of layers should be somewhere between 2 to 4. Then sampling uniformly at random among 2, 3, and 4 might be reasonable, or even using a grid search where you explicitly evaluate the values 2, 3, and 4 might be reasonable. So these were a couple examples where sampling at uniformly at random over the range you're contemplating might be a reasonable thing to do. But this is not true for all hyperparameters. Let's look at another example. Say you're searching for the hyperparameter alpha, the learning rate, and let's say that you suspect 0.0001 might be on the low end, or maybe it could be as high as 1. Now, if you draw the number line from 0.0001 to 1 and sample values at random, uniformly at random over this number line, or about 90% of the values you sample will be between 0.1 and 1. So you're using 90% of the resources to search between 0.1 and 1, and only 10% of the resources to search between 0.0001 and 0.1. So that doesn't seem right. Instead, it seems more reasonable to search for hyperparameters on a log scale, where instead of using a linear scale, you'd have 0. 0.0001 here, and then 0.001, 0.01, 0.1, and then 1. And you instead sample uniformly at random on this type of logarithmic scale. Now you have more resources dedicated to searching between 0.0001 and 0.001, and between 0.001 and 0.01, and so on. So in Python, the way you implement this is let r equals -4, times np.random.rand. And then a randomly chosen value of alpha would be alpha equals 10 to the power of r. So after this first line, r will be a random number between -4 and 0. And so alpha here will be between 10 to the -4 and 10 to the 0. So 10 to the -4 is this left thing, this 10 to the -4. And 1 is 10 to the 0. In a more general case, if you're trying to sample between 10 to the a to 10 to the b on the log scale. And in this example, this is 10 to the a, and you can figure out what a is by taking the log base 10 of 0.0001, which is going to tell you a is -4. And this value on the right, this is 10 to the b, and you can figure out what b is by taking log base 10 of 1, which tells you b is equal to 0. So what you do is then sample r uniformly at random between a and b. So in this case, r would be between -4 and 0, and you can set alpha, or your randomly sample hyperparameter value, as 10 to the r. Okay, so just to recap, to sample on the log scale, you take the low value, take logs to figure out what is a, take the high value, take a log to figure out what is b. So you're now trying to sample from 10 to the a to 10 to the b on a log scale. So you set r uniformly at random hyperparameter value as 10 to the r. Okay, so just to recap, to sample on the log scale, you take the low value, take logs to figure out what is a, take the high value, take a log to figure out what is b. So you're now trying to sample from 10 to the a to 10 to the b on a log scale. So you set r uniformly at random between a and b, and then you set the hyperparameter to be 10 to the r. So that's how you implement sampling on this logarithmic scale. Finally, one other tricky case is sampling the hyperparameter beta use for computing exponentially weighted averages. So let's say you suspect that beta should be somewhere between 0.9 to 0.999. Maybe this is the range of values you want to search over. So remember that when computing exponentially weighted averages, using 0.9 is like averaging over the last 10 values, kind of like taking the average of 10 days temperature, whereas using 0.999 is like averaging over the last 1,000 values. So similar to what we saw on the last slide, if you want to search between 0.9 and 0.999, it doesn't make sense to sample on a linear scale, right? Uniformly at random between 0.9 and 0.999. So a better way to think about this is that we want to explore the range of values for 1 minus beta, which is going to now range from 0.1 to 0.001. And so we'll sample between beta, take on values from 0.1 to maybe 0.1 to 0.001. So using the method we had figured out on the previous slide, this is 10 to the minus 1, this is 10 to the minus 3. Notice on the previous slide we had the small value on the left and the large value on the right, but here we have a reverse. We have the large value on the left and the small value on the right. So what you do is you sample R uniformly at random from -3 to -1, and you set 1 minus beta equals 10 to the R, and so beta equals 1 minus 10 to the R, and this becomes a randomly sampled value of your hyperparameter chosen on the appropriate scale. And hopefully this makes sense in that this way you spend as much resources exploring the range 0.9 to 0.99 as you would exploring 0.99 to 0.999. So if you want a slightly more formal mathematical justification for why we're doing this, right? Why is it such a bad idea to sample on a linear scale? It is that when beta is close to 1, the sensitivity of the results you get changes even with very small changes to beta. So if beta goes from 0.9 to 0.9005, it's no big deal. This is hardly any change in your results. But if beta goes from 0.999 to 0.9995, this will have a huge impact on exam. exactly what your algorithm is doing, right? In both of these cases, it's averaging over roughly 10 values, but here it's gone from an exponentially weighted average over about 1,000, the last 1,000 examples to now the last 2,000 examples. And it's because that formula we had, 1 over 1 minus beta, this is very sensitive to small changes in beta when beta is close to 1. So what this whole sampling process does is it causes you to sample more densely in the regime of when beta is close to 1, or alternatively, when 1 minus beta is close to 0, so that you can be more efficient in terms of how you distribute the samples to explore the space of possible outcomes more efficiently. So I hope this helps you select the right scale on which to sample the hyperparameters. In case you don't end up making the right scaling decision on some hyperparameter choice, don't worry too much about it. Even if you sample on a uniform scale where some other scale would have been superior, you might still get okay results, especially if you use a coarse-to-fine search, so that in later iterations, you focus in more on the most useful range of hyperparameter values to sample. I hope this helps you with your hyperparameter search. In the next video, I also want to share with you some thoughts on how to organize your hyperparameter search process that I hope will make your workflow a bit more efficient. You've now heard a lot about how to search for good hyperparameters. Before wrapping up our discussion on hyperparameter search, I want to share with you just a couple final tips and tricks for how to organize your hyperparameter search process. Deep learning today is applied to many different application areas, and that intuitions about hyperparameter settings from one application area may or may not transfer to a different one. There is a lot of cross-fertilization among different applications domains. So for example, I've seen ideas developed in the computer vision community, such as ConvNets or ResNets, which we'll talk about in a later course, successfully applied to speech. And I've seen ideas that were first developed in speech successfully applied in NLP, and so on. So one nice development in deep learning is that people from different application domains do read increasingly research papers from other application domains to look for inspiration for cross-fertilization. In terms of your setting for the hyperparameters though, I've seen that intuitions do get stale. So even if you work on just one problem, say logistics, you might have found a good setting for the hyperparameters and kept on developing your algorithm, or maybe seen your data gradually change over a course of several months, or maybe just upgraded the servers in your data center. And because of those changes, the best setting of your hyperparameters can get stale. So I recommend maybe just retesting or re-evaluating your hyperparameters at least once every several months to make sure that you're still happy with the values you have. Finally, in terms of how people go about searching for hyperparameters, I see maybe two major schools of thought, or maybe two major different ways in which people go about it. One way is if you babysit one model, and usually you do this if you have maybe a huge data set, but not a lot of computational resources, not a lot of CPUs and GPUs, so you can basically afford to train only one model or a very small number of models at a time. In that case, you might gradually babysit that model even as it's training. So for example, on day 0, you might initialize your parameters as random and then start training. And then you gradually watch your learning curve, maybe the cost function J or your depth set error or something else, gradually decrease over the first day. Then at the end of day 1, you might say, gee, it looks like it's learning quite well. I'm going to try increasing the learning rate a little bit and see how it does. And then maybe it does better, and then that's your day 2 performance. And after 2 days, you say, oh, okay, still doing quite well. Maybe I'll further the momentum term a bit or decrease the learning rate a little bit now. And then you're now into day 3. And every day you kind of look at it and try nudging up and down your parameters. And maybe on one day you found your learning rate was too big, so you might go back to the previous day's model and so on. But you're kind of babysitting the model one day at a time, even as a training over a course of many days or over the course of several different weeks. So that's one approach, and people that babysit one model, that is watching it perform. Before wrapping up, two major different ways in which people go about it. One way is if you babysit one model, and usually you do this if you have maybe a huge data set, but not a lot of computational resources, not a lot of CPUs and GPUs, so you can basically afford to train only one model or a very small number of models at a time. In that case, you might gradually babysit that model. You might say, try nudge one day at a time, even as a training over a course of one approach. And people that babysit one model, that is watching performance and patiently nudging the learning rate up or down, that's usually what happens if you don't have enough computational capacity to train a lot of models at the same time. The other approach would be if you train many models in parallel. So you might have some setting of the hyperparameters and just let it run by itself, either for a day or even for multiple days. Maybe get some learning curve like that. And this could be a plot of the cost function j, or cost of your training error, or cost of your dev set error, but some metric that you're tracking. And then at the same time, you might start up a different model with a different setting of the hyperparameters. And so your second model might generate a different learning curve, maybe one that looks like that, or looks like that one looks better. And at the same time, you might train a third model, which might generate a learning curve that looks like that. And another one that maybe this one diverges, so it looks like that, and so on. But you might train many different models in parallel, where these orange lines are different models, right? And so this way you can try a lot of different hyperparameter settings and then just maybe quickly at the end pick the one that works best. It looks like in this example, it was maybe this curve that looked best. So to make an analogy, I'm going to call the approach on the left the panda approach. When pandas have children, they have very few children, usually one child at a time, and then they really put a lot of effort into making sure that the baby panda survives. So that's really babysitting, one model or one baby panda. Whereas the approach on the right is more like what fish do. I'm going to call this the caviar strategy. There's some fish that lay over 100 million eggs in one season, in one mating season. But the way fish reproduce is they lay a lot of eggs and don't pay too much attention to any one of them, but just see that hopefully one of them or maybe a bunch of them will do well. So I guess this is really the difference between how mammals reproduce versus how fish and a lot of reptiles reproduce. But I'm going to call it the panda approach versus the caviar approach, since that's more fun and memorable. So the way to choose between these two approaches is really a function of how much computational resources you have. If you have enough computers to train a lot of models in parallel, then by all means take the caviar approach and try a lot of different hyperparameters and see what works. But in some application domains, I see this in some online advertising settings as well as in some computer vision applications where there's just so much data and the models you want to train are so big that it's difficult to train a lot of models at the same time. It's really application dependent, of course, but I've seen those communities use the panda approach a little bit more, where you're kind of babying a single model along and nudging the parameters up and down and trying to make this one model, work. Although, of course, the panda approach, having trained one model and then seeing it work or not work, maybe in the second week or the third week, maybe you actually initialize a different model and then, baby that one along. Just like even pandas, I guess, can have multiple children in their lifetime, even if they have only one or a very small number of children at any one time. So hopefully this gives you a good sense of how to go about the hyperparameter search process. Now, it turns out that there's one other technique that can make your neural network much more robust to the choice of hyperparameters. It doesn't work for all neural networks, but when it does, it can make the hyperparameter search much easier and also make training go much faster. Let's talk about this technique in the next video.
Okay, before going to end up the recording, let's read the first. What I'm learning today is hyperparameter tuning, deep neural network, which is about okay. So we will uh, we learned many optimization algorithms in the first week and two second week so far. And there was a lot of hyperparameters like learning rate and beta in the exponentially averaged weights in the momentum algorithm and the RMS probe and ADAM algorithm. And also there was a number of layers and number of hidden units, which we already seen in the first course in the deep neural network. And the another algorithm, we saw the learning rate decay. And also there was a mini batch method, which we partitioned the whole batch into separate batches. The professor just advised that the learning rate is the most important hyperparameter, and then the beta and number of layers and mini batch size is a second important. The other thing is quite the constant, and if there was no huge impact on the changes of the important hyperparameters, then after that we can change these least important hyperparameters again. Then we can think about the choose the hyperparameter values, about the how to choose. But we don't do that in the grid cell. Like let's take an example that the vertical axis is corresponded to learning rate and the horizontal axis is corresponded to epsilon. Then we have five different values of learning rate and five different values on epsilon. And why we change the learning rate in the five different values? Although we change the values of epsilon, it maybe does not have a huge impact on the learning effect, uh, actually. So in this case, we'd better to choose random points, generate random points and choose among them. Because we can have 55 different values of hyperparameters and 55 different values of mm, epsilons in this case. Once we got a few points that work well in our model, and we can shrink the area of search slightly because it's called as close to find. And let's assume that we find a blue circled points is works well in our model, and we can shrink the mean zoom in the area of search like this small area, and we can sample again in this model, which is more density, has more density rather than this the original area of search. Then we can more tune the hyperparameters uh, as in the process of searching the hyperparameter. Next topic is about using an appropriate scale to pick hyperparameters. That about the number of layers and hidden units, you'd be okay to choose just uniform randomly generated points in the range. But about the learning rate, it may be not good choice. It may be not good choice. So that let's take an example. We have a learning rate from range between 0.1 and no 0.0001 and 1. In this case, by 5% chances we get have a value between this the lowest value to 0.1. and it's unfair to because it may be better just uniformly random pick the random value between the partitioned first in the low scale. Uh, to take a low scale of the original range, we can follow this formula. We take the lowest value first, and then we take the log, and we can find the what is the a. We do the same things for the high value, and we can get out the what is corresponding to b. So we can make a random number between a and b, and then we can use that for to pick the actual hyperparameter value. And the way to pick hyperparameter for exponentially weighted averages is follow the same steps. Uh, the intuition for the y linear scale is quite bad to use because as you can see, the when the beta is 0.9 and 0.9 compared to 0.905, it has no huge impact on the learning process. But in another case, because we the beta implies the 1 over 1 minus beta 1 over 1 minus beta days. So when we have a 0.999 is corresponding to 1000 days, but 0.9995 is corresponding to 5000 days, which is 5 times bigger. The previous one is two huge impacts. So it may be good to use a low scale in this case. Next thing is the few advice for hyperparameter tuning in practice. The first one is retest hyperparameters occasionally, where we going to learn our model. And when we have a large data set but don't have lots of computational resources like GPU and CPU, it may be better to use a babysitting model, one babysitting method, because like Panda doesn't have a lot of babies. Uh, they generally have a few number of babies, and we can just watching how our model to learn the data set, and we can just tune day by day, like babysitting as it were. In another case, we can take an approach the training many models in parallel way is that try different hyperparameters at the same time on different models, like how fish reproduce their babies. So this is end of today's recording, and thanks for watching.